Solicited Part 2, presented by G. Satyanarayana Gaud, Assistant Professor, Department of Chemistry, Dr. BRR Government College, Jarchalla. In this discussion, we learn about space lattice or crystal lattice, types of unit cells, Bravaise lattices, and X-ray diffraction. What is the meaning of space lattice or lattice? Space lattice or lattice means the regular pattern of points which describe the three-dimensional arrangement of particles in a crystal structure is called space lattice or crystal lattice. We have already discussed about the differences between crystalline solids and amorphous solids. In crystalline solids, the constant particles are arranged in regular, definite three-dimensional fashion. Is it? So, the arrangement of regular three-dimensional fashion of the particles in a space is called space lattice or lattice. In this, each point represents a molecule or atom or ion or group of any of these. Means a space lattice is indicated with help of the diagram as points. Each point is called as lattice point. This point indicates what? It indicates a molecule or atom or ion. Suppose it's the ice. We are representing the space lattice of ice. That each point representing the diagram of the ice crystal that represent molecule. Similarly, if quartz is represented, in that quartz, silica and oxygen atoms are the constant particles. Each point represents silica or oxygen like that. In sodium chloride space lattice, Na plus and Cl minus ions are arranged in three-dimensional fashion. So each point, lattice point, is represented with what? That Cl minus R, that is representing Cl minus or Na plus. So space lattice is nothing but it is the repetition of unit cell in three-dimensional fashion. Hence, a crystal lattice or space lattice is formed, constituted with the help of the unit cells. Means if you arrange the unit cells in three-dimensional fashion, that gives us the space lattice or lattice. Means the unit cell is the one of the parts of the space lattice. It's a basic part. We say it is a basic part. So when you are arranging these unit cells in three-dimensional fashion, that gives the space lattice or lattice. How the unit cell is forming? Again, the unit cell is forming by arrangement of lattice points. Means what is unit cell, let me say? Is it clear what is the meaning of space lattice? It is a regular three-dimensional arrangement of particles of a crystal in a space. That is called space lattice or lattice. How the space lattice is developed? Space lattice is developed by arrangement of unit cells in three-dimensional fashion. So unit cell means a smallest portion of the space lattice which can generate a complete crystal by repeating its own dimensions in various directions is called unit cell. Means it is one of the basic unit. It is one of the three-dimensional basic unit which is present in the space lattice. Repetition arrangement of this base unit in three-dimensional fashion that gives us the space lattice or lattice. There's a difference between the space lattice and unit cell. Let me see this diagram where this is representing the crystal lattice. In that crystal lattice, this totally it is representing the crystal lattice. In this crystal lattice, you see this is one part is representing what? Unit cell. For example, a wall is the crystal lattice. Now that wall is constructed with what? Bricks. If you are arranging the bricks in three-dimensional fashion, so that formation of wall takes place, construction of wall takes place. Like that, each brick now it represents a unit cell. So unit cell is a three-dimensional part, a basic part, which is repeatedly arranged to give a crystal lattice. That is the meaning of unit cell and space lattice, you can see. Okay, next let me discuss about the types of unit cells. Cubic unit cells are available only in three types. Cubic unit cells means we know the dimensions of the unit cells. Two types of dimensions we call. One is the intercepts of the planes on the planes or the faces on XYZ standard axis. They are represented by A, B, and C. And also the interfacial angles, that is alpha, beta, and gamma. We call them as what? The angles made by the planes of the crystal on standard axis, alpha, beta, and gamma. So in case of the cubic unit cell, we know that alpha is equal to beta is equal to gamma is equal to 90 degrees. And also we know A is equal to B is equal to C like. So in the cubic system, unit cell, if we talk, these containing only three types of unit cells. It is a simple cubic, okay. Next, face-centered cubic. Second, third is a body-centered cubic. Means depending on the arrangement of lattice points. We know what is the meaning of lattice point. Lattice point may be the atom, it may be the molecule, or it may be the ion. Depending on the arrangement of lattice points, these types are classified. How? They are classified as simple cubic, face-centered cubic, body-centered cubic. Another type of unit cell is also present. That is what we call it is end-centered unit cell. End-centered unit cell. But it does not belongs to the cubic system. It does not belongs to cubic system. So depending on the arrangement of lattice points, cubic systems are available in three forms: simple cubic, face-centered cubic, body-centered cubic. Fourth one is also available, that is what? End-centered cubic cell. But this end-centered cubic cell does not belongs to cubic system. Okay, let us discuss about these types. Simple unit cell. It is also called as primitive unit cell. How it will be? It is that like this is lattice points are arranged only at corners of the unit cell. We know that a cube is having 8 corners. That is, each corner is occupied by a lattice point. Each corner will be occupied by the lattice point. Here you can see 8 corners. Each corner is occupied by lattice points. Is it? So this represents the primitive, or we say it is simple cubic or simple unit cell, primitive unit cell. 8 corners are there. 8 corners are occupied by the lattice points. But if we see in the space lattice or crystal lattice, we know that if these unit cells are repeatedly arranged in three-dimensional fashion, it gives a space lattice or crystal lattice. When you are arranging these unit cells in three-dimensional fashion repeatedly, then these lattice points which are present at corners are shared by 8 unit cells. Suppose you see one of the unit cell. So one of the unit cell. This is the lattice point which is present at corner. Now this lattice point will be shared by how many? It will be shared by 8 unit cells. Means this lattice point is common for 8 unit cells. Is it? Here you can see that how it is divided. Is it? It is divided like this. Is it? It is 1/8 part that belongs to this unit cell. Here you can also see very clearly. So from each corner, what is the contribution of that lattice point towards this unit cell? What is the contribution of that lattice point towards this unit cell? It is 1/8. What is the reason? Because this corner is shared by 8 unit cells in the crystal lattice. It is shared by 8 unit cells. That's why if you calculate the average contribution towards one unit cell, it will be 1/8. Mean from each corner we will get 1/8 contribution. Like that, how many corners are there? 8 corners are there. That's why the average number of lattice points in this simple unit cell, or you say primitive unit cell, will be equal to 8 into 1 by 8, that gives 1. Means if we see the simple unit cell, what will be the weight of a simple unit cell? It is nothing but the weight of one lattice point. It is the weight of one lattice point. For example, M is a metal which is present in the form of simple cubic. Then what will be the weight of the unit cell? Means what we say? It is nothing but weight of one atom of metal. Because you see 8 atoms of metals are arranged at 8 corners. The contribution from each corner is 1 by 8. Like that 8 corners are there. That's why total contribution will be equal to 8 into 1 by 8. So that we will get 1. That is the average number of lattice points present per unit cell. So in simple cubic unit cell, how it will be? 8 corners are occupied by the lattice points. And what will be the average number of lattice points per unit cell? It is equal to 1. It is 8 into 1 by 8, that is equal to 1. Second one, you see the face-centered unit cell. What is the meaning of face-centered unit cell? This is a unit cell which is containing lattice point at all 8 corners. Okay, all 8 corners. You can see here 1, 2, 3, next 4, 5, 6, and 7. Here it is 8. Like that, 8 corners. And also the lattice points will be present at center of faces. You know, a cubic system, a cubic structure will have 6 faces. 8 corners, 6 faces. Each center of face will have a lattice point. You see, one lattice point. The second one, second face, you see. Here you can see the third one. Okay, this is fourth one. Is it? Front will be also there. Fifth and sixth will be there. Front will be also there. Is it? It is not represented here. Is it? Front will be also there. Here it is. Sorry, here. So total it will be equal to how many? 6 center of faces will have that last one. 6 center of faces will have that one. Okay. So like that 1, 2, 3, 4, 5, 6. 6 will have those lattice one. Like this, a face-centered unit cell means it is a cubic cell or the unit cell which is containing the lattice points at 8 corners and 6 centers of faces. You can see the 6 centers of faces. 1, here it is 2, it is 3, next 4, next 5, 6, like this. Okay, next, what will be the average number of lattice points per unit cell of face-centered unit cell? Now you can see how many corners are occupied? 8 corners. Just now we have discussed. A unit cell which is present at corner will contribute 1 by 8 part towards that unit cell. So the average number of lattice point from corners, the contribution towards corners will be equal to contribution towards from the corner will be equal to 8 into 1 by 8. And when a lattice point is present in the center of the face, here you can see it represented the center of face. Only 2 unit cell will share this lattice point. That's why the contribution per unit cell will be equal to 1 by 2. Half belongs to this unit cell and half belongs to the adjacent unit cell. Because this lattice point is common to 2 unit cells when the unit cells are arranged side by side. So a lattice point which is present at center of face will contribute 1 by 2 because that will be shared by 2 unit cells. So how many face centers are there? 6. That's why 6 into 1 by 2. So 8 into 1 by 8 is from corners and 6 into 1 by 2 will be from faces. It will be equal to 1 plus 3, 4. The average number of lattice points present per face-centered unit cell will be equal to 4. Is it? In the case of simple cubic, what to say? It was 1. Now we are saying it is equal to 4 in the case of face-centered cubic cell. Next, you see the body-centered unit cell. What is the meaning of body-centered unit cell? The lattice points are present at corners and also present at center of body. Also present at center of body. 1, it is 2, 3, 4, 5, 6, 7, and 8. 8 corners. And also you can see the center of body. Lattice points are also present in the center of body. That is called body-centered unit cell. 8 corners and center of body will be occupied by the lattice points. Okay. Next, what is the average number of lattice points present per unit cell? Here you can see when a lattice point is present in the corner, only 1 by 8 will be shared by from each corner or contributed from each corner. Like that, how many corners are there? 8 corners are there. So 8 into 1 by 8. Okay, then the center of body. The center of body it clearly belongs to only one unit cell, this unit cell only. No any other unit cell will share it because it is present in the inside of the body. Okay, so average number of lattice point per unit cell will be, now you see, 8 into 1 by 8 plus 1 into 1, that is equal to what? It is 2. Okay, this is the average number of lattice point present per unit cell, is it? Okay, like this we have discussed the 3 types, is it? 3 types. Next you can see the 4th type, end-centered unit cell, but this is not belongs to the cubic system. What is the meaning of end-centered unit cell? End-centered unit cell means the lattice points are present at the corners, 8 corners. Okay, and addition to that, 8 corners you can see here, 8 corners. Here also one should be there, is it? It is missing. Is it lattice point should be there here, is it? The lattice point is also present here. They are missing here. Okay. Next, 8 corners. In addition to that, what? Any 2 opposite faces. You see, this one and this one. 2 opposite faces. That is called end-centered unit cell. End-centered unit cell. So it is containing what? 8 corners. Lattice points at 8 corners and any 2 opposite faces. Centers of any 2 opposite faces. Any 2 opposite faces. That is called end-centered unit cell. Can you calculate the average number here? The average number will be equal to 8 corners means 8 into 1 by 8, 1. 2 centers of faces, 2 into 1 by 2, 1. So 1 plus 1, average number will be 2, is it? So the average number of lattice point per unit cell will be equal to 2. Like this, in the case of simple cubic, only 8 corners are occupied by the lattice points. Average number will be 1. In the case of face-centered unit cell, 8 corners will be occupied by the lattice points. In addition to that, 6 centers of faces also. The average number of lattice point per unit cell will be 4. In the case of body-centered unit cell, 8 corners are occupied by the lattice points and the center of body is also occupied by the lattice points. The average number will be equal to 2. End-centered unit cell does not belong to cubic system. 8 corners will be occupied by the lattice points and any 2 opposite faces will contain the lattice points. That we call it as end-centered unit cell. There are the types of unit cells that is classified based on the position of what lattice points. Next we say the classification of crystals by shapes. The shape of any unit cell that depends on 2 types of parameters. One we say it is the intercepts made on standard axis ABC, mean the intercepts of the planes of the unit cell on standard axis XYZ. They're called A, B and C. They are intercepts on x-axis, on y-axis and z-axis respectively, and also interfacial angles alpha, beta and gamma. For example, in the case of cubic system, A is equal to B is equal to C we say, and alpha is equal to beta is equal to gamma, like that is it? Here you can see what is the intercept on x-axis. It is A, and y-axis it is B, and z-axis it is C. So they are the interfacial angles alpha, next it is beta, and this is gamma. Depending on these parameters, the shape of the unit cell will depend. Okay, so like this, based on these, now we can discuss about the Bravaise lattices. What are Bravaise lattices? In 1848, the French crystallographer, he showed that the geometrical shapes are there only 14 different ways. the geometrical shapes, that there are only 14 different ways in which similar points can be arranged in three-dimensional fashion. When we arrange the similar points in three-dimensional fashion, we can arrange in 14 different ways only. He proved that. Actually, 232 groups of arrangements are there in the crystal system, but all of them are regrouped, and finally it was observed that 14 different ways in which similar points can be arranged in three-dimensional space. These 14 different ways which we are arranging the similar points are nothing but Bravaise lattices. So the total number of space lattices belongs to all 7 basic crystal systems. The crystal systems are 232 regrouped into 7 systems finally. The 7 basic crystal systems are now totally containing 14 types of arrangements. These 14 types of arrangements are called as Bravaise lattices. So how many crystal systems are there? 7 crystal systems are there. How many ways we can arrange in all these 7 crystal systems? It will be 14. So we say this 14 is the Bravaise lattices we call it. Let me discuss about the Bravaise lattices. So 7 crystal systems and Bravaise lattices. Among these, first crystal system is regular or cubic system. What is meaning of regular or cubic system? We know the parameters of that unit cell. It is equal to A is equal to B is equal to, what we say it is, C is it. A is equal to B is equal to C. Means interplanar distance, intercepts on x, y axis will be same, is it? And also we say alpha, beta, gamma is equal to 90 degrees. Now this crystal system is available in the nature in 3 Bravaise lattices. Only in 3 Bravaise lattices. What they are? Simple or primitive, we say. How it will be? 8 corners are occupied by the lattice points, you can see here. Second is available in the form of body-centered cubic cell. How it is present? You can see here, body-centered, 8 corners and the center of body. Third is as face-centered, 8 corners and 6 centers of faces. So this we call it as what? A regular or cubic system. It is the first type of crystal system. It is available in the nature in 3 forms. It may be the simple or primitive, or it may be the body-centered, or it may be the face-centered. 3 types are available there. Is it? Next, the second crystal system is orthorhombic or orthorhombic crystal system. What are the parameters? You see, A is equal to B, A is not equal to B is not equal to C, but alpha, beta, gamma are exactly equal to 90 degrees. Dimensions are A is not equal to B is not equal to C, and alpha, beta, gamma is equal to 90 degrees. Now this crystal system is available, observed in 4 forms. One is simple system, and body-centered system, and face-centered unit cell, and end or base-centered. Is it? Primitive unit cell, body-centered unit cell, face-centered unit cell, and end or base-centered. Here you can see it is simple, whereas it is end-centered or base-centered. Okay, whereas this is a body-centered, this is a face-centered. So orthorhombic crystal system is having the 4 Bravaise lattices, whereas cubic crystal system is having only 3 Bravaise lattices. 3. Here it is containing 4 Bravaise lattices. These 4 are the different ways of arrangement of lattice points. So the orthorhombic crystal system is having the highest number of Bravaise lattices. It is equal to 4. Okay. Next you see the third one. Third is the tetragonal crystal system. Tetragonal crystal system. What are the dimensions or parameters? The dimensions are A is equal to B not equal to C, and alpha, beta, gamma is equal to 90 degrees. A is equal to B not equal to C, and alpha is equal to beta is equal to gamma is equal to 90 degrees. This is available only in 2 forms, that is simple system and body-centered unit cell. a primitive unit cell and body centered unit cell. Only two Bravaise lattices are present in tetragonal. What are the dimensions? A is equal to B, not equal to C. How the interfacial angles? Alpha is equal to beta is equal to gamma, that is equal to 90 degrees. Here you can see this is a simple system, that is simple unit cell, whereas this is the body centered unit cell. Next you see the monoclinic crystal system, fourth one. What are the dimensions of the monoclinic? A is not equal to B is not equal to C, and alpha beta 90 degrees, gamma is not equal to 90 degrees. That is monoclinic crystal system. Sometimes here we say alpha is equal to gamma is equal to 90 degrees, beta is not equal to 90 degrees. Like that also we say. So it contains only two Bravaise lattices. Only two Bravaise lattices. One is a simple system. This is wrongly spelled, sorry. This is not body centered. It will be the end centered, we say. It will be the end centered, not body centered. It is the end centered. Only two Bravaise lattices are present. One is a simple or primitive unit cell. Second is the end centered. Is it? Here you can see very clearly end centered. Whereas this is a simple or primitive. Simple or primitive. So what are the dimensions? Alpha is equal to beta is equal to 90 degrees. Gamma is not equal to 90 degrees. Where A is not equal to B is not equal to C. How many Bravaise lattices are there? Only two. What they are? Either primitive or it's simple you say. Second is end centered, is not the body centered. You remember that is it. Next, go for the fifth one, triclinic crystal system. The most unsymmetric we say it is. Why it is more unsymmetric? Because the dimensions are like this. A is not equal to B is not equal to C, and also alpha is not equal to beta is not equal to gamma, that is not equal to 90 degrees. It contains only one Bravaise lattice, that is only simple system. A simple unit cell will be present. There is simple unit cell. You can see this simple unit cell. Alpha, beta, gamma is not equal to 90 degrees. Only one Bravaise lattice is there in the triclinic crystal system. Sixth one is the hexagonal crystal system. Here the dimensions are A is equal to B but not equal to C, and alpha, beta, alpha is not equal to beta, that is 90 degrees, whereas gamma is equal to 90 degrees. Again, this is here it should be what alpha is equal to beta is equal to 90 degrees, but gamma is not equal to 90 degrees. You remember this will be equal to 120 degrees. It is not equal to 90 degrees means it will be 120 degrees. So what are the dimensions? It is A is equal to B but not equal to C first. What are the angles? Alpha is equal to beta is equal to 90 degrees, but gamma is equal to 120 degrees. It also contains only one Bravaise lattice, that we call it as a simple unit cell. Here you can see the simple unit cell is it. Simple unit cell. This will be 120 degrees. Okay. Next you see the seventh one, rhombohedral or trigonal. Rhombohedral or trigonal, in this the dimensions are A is equal to B is equal to C, means all sides are equal. But alpha, beta, gamma is not equal to 90 degrees. It contains only one Bravaise lattice, that we say it is simple. Only one Bravaise lattice is there. It is rhombohedral or trigonal. Can you say what is the type of the crystal system where A is not equal to B is not equal to C and alpha, beta, gamma is 90 degrees? What type of unit cell we said? It is orthorhombic. So rhombohedral and orthorhombic, you can see this difference. In the case of orthorhombic, is it here you see A is not equal to B is not equal to C, but alpha, beta, gamma 90 degrees. Whereas in the case of rhombohedral, A is equal to B is equal to C, but alpha, beta, gamma not equal to 90 degrees. This is orthorhombic and rhombohedral difference you can see. Like this, 7 crystal systems are there. All these 7 crystal systems are available in different forms. Here you can see the 7 crystals total cubic. In the case of cubic, is it what are the dimensions? A is equal to B is equal to C, alpha, beta, gamma 90 degrees. How many Bravaise lattices? They are nothing but Bravaise lattices. How many Bravaise lattices are there? So 3 Bravaise lattices: primitive, body-centered, face-centered. That are the examples of the crystal systems. Tetragonal, A is equal to B, not equal to C, alpha, beta, gamma 90 degrees. It is available only in 2 Bravaise lattices. Third one is orthorhombic, A is not equal to B, is not equal to C, alpha, beta, gamma 90 degrees. So it is available in the four Bravaise lattices: primitive, body-centered, face-centered, end-centered. Potassium nitrate and barium sulfate are the example for it. Hexagonal crystal system, A is equal to B but not equal to C. Alpha beta is 90 degrees but gamma is 120 degrees, only available in one Bravaise lattices. Example, magnesium and zinc oxide. Trigonal or rhombohedral, you see. A is equal to B is equal to C but alpha beta gamma not equal to 90 degrees. Available with only one Bravaise lattice. Examples are the calcite, means calcium carbonate, mercuric sulfide. It is also called cinnabar. Cinnabar is a common name. Sixth one is a monoclinic. Dimensions: A is not equal to B is not equal to C, where alpha is equal to gamma is equal to 90 degrees, beta not equal to 90 degrees. This also can be written as alpha beta is equal to 90 degrees, gamma is not equal to 90 degrees, like that. It is available in 2 forms, primitive or end-centered. Examples are monoclinic sulfur, one of the allotropic form of the sulfur, and sodium sulfate, hydrated sodium sulfate, decahydrated sodium sulfate. Seventh one is triclinic system. A is not equal to B is not equal to C, and alpha, beta, gamma not equal to 90 degrees. Alpha is not equal to beta, not equal to gamma, not equal to 90 degrees. Available only in one primitive form, one Bravaise lattice, that is primitive. Examples are potassium dichromate and orthoboric acid. Like this, if you see the total number of Bravaise lattices, here it will be 3, whereas it is 2. Okay, here you can see it is 4 and 1 and 1 and 2, 1. Total you will get 14. 14 Bravaise lattices you will get. So 7 crystal systems are available in 14 Bravaise lattices. In this, the crystal system which is containing highest number of Bravaise lattices is orthorhombic. Most unsymmetric crystal system is triclinic. Like that, we can frame many questions on this table. So please remember these dimensions as well as examples and Bravaise lattices of concerned crystal system. Okay, this is about the space lattice, crystal lattice, types of unit cells, and Bravaise lattices. Next, X-ray diffraction. In the beginning, we were discussing that only the crystal systems will provide the X-ray diffraction bands, not the amorphous solids, because these crystalline solids are containing the planes. When X-rays are allowed to diffract on the planes of the crystal, they produces the diffraction bands. This was first observed by a German scientist, Max von Laue. He suggested that why only the crystals are producing X-ray diffraction bands. Means the radiation used is only the X-rays. Why only the X-rays are diffracted from the crystalline planes, not any other electromagnetic radiation like UV or visible or IR. He said, Max von Laue suggested that the wavelength of X-ray, this is important, is it? The wavelength of X-rays are in the same order as that of the interatomic distance in the crystal. Mean the interplanar distance, we say like this, the interplanar distance in the crystalline solid is matching with what? The wavelength of X-rays. The wavelength of X-rays and interplanar distance in the crystalline solids. Both of these are matching, means both of these are approximately in the same order. That's why the X-rays are only providing the X-ray diffraction bands from the crystalline solids. So you also remember Van Loo is awarded 1914 Nobel Prize in Physics, remember. So after this, you see, W.H. Braggs and W.L. Braggs also got Nobel Prize, and they succeeded in diffracting the X-rays from sodium chloride crystal system. So why the crystalline solids will only provide the diffraction bands? Because the interplanar distance in the crystalline solid and the wavelength of X-rays will be in the same order. That is the reason why the X-ray diffractions will be observed in the case of crystalline solids. Okay, so like this we have discussed in this discussion what is meaning of that is unit cell and space lattice, crystalline lattice, crystal lattice, types of unit cell depending on the lattice points positions. We have also calculated the average number of lattice points present per unit cell. Next, we have discussed the 7 crystal systems, and Bravaise lattices belongs to the 7 crystal systems, and also why only the crystalline solids produces diffraction bands. Thank you.